We harvested the frog's sciatic nerve and gastrocnemius muscle and placed it in the nerve chamber. The compound action potential, or CAP, was recorded monophasically, and the compound muscle action potential, or MAP, was recorded biphasically. This buildup initiates an action potential, which regenerates itself as it travels down the axon, known as saltatory conduction. As the action potential moves unidirectionally, it depolarizes the membrane, causing voltage-gated sodium channels to open and sodium influx at nodes of Ranvier. It eventually reaches the presynaptic axon terminal, where the depolarization causes PQ-type calcium channels to open. Calcium influx occurs through these channels, and these ions trigger exocytosis of vesicles containing acetylcholine. Acetylcholine diffuses quickly across the cleft to bind to nicotinic cholinergic receptors on the postsynaptic muscle membrane. These nicotinic cholinergic receptors are mixed cation channels. The magnitude of the EPP is dependent on the number of nicotinic cholinergic receptors activated by acetylcholine. If the EPP is high enough, voltage-gated sodium channels on the muscle membrane will open to allow even more sodium influx. This will trigger a muscle action potential, which can lead to a contraction. In clinical settings, atropine is used as a muscarinic cholinergic receptor blocker and can be used to treat bradycardia by blocking the effects of the parasympathetic nervous system. Since there are no muscarinic receptors located in the neuromuscular junction, we expect that atropine would have no effect on threshold, maximum MAP amplitude, or synaptic delay. However, our results show that the maximum MAP amplitude dropped from 11.75 millivolts to 7.55 millivolts after atropine was added, and the synaptic delay increased from 2.91 milliseconds to 3.02 milliseconds. Obviously, atropine's clinical mechanism of action cannot be used to explain these results. Studies have shown that atropine also inhibits nicotinic cholinergic receptors located in the postsynaptic terminal. Inhibition of these receptors decreases the amount of sodium ions that flow into the postsynaptic terminal. With a decreased amount of sodium influx, the magnitude of the end plate potential is smaller than control, so there is a smaller depolarizing force driving membrane potential to threshold. In muscle cells with a higher resting potential, this force is still able to depolarize and open enough voltage-gated sodium channels to initiate an action potential. In muscle cells with a lower resting potential, this force is not enough to generate an action potential. So some muscle cells do not fire action potentials, which is why the amplitude of the MAP decreases. In addition, since there are fewer nicotinic cholinergic receptors open, the rate at which sodium flows into the postsynaptic terminal is slower, so it takes longer for enough positive charge to build up to initiate an action potential. This increases MAP latency, which is why synaptic delay also increases. In clinical settings, adenosine is an antiarrhythmic agent typically used to treat tachycardia. In our results, after adenosine was added to the neuromuscular junction, the maximum MAP amplitude dropped from 7.61 millivolts in the control to 4.745 millivolts, and the synaptic delay increased from 2.97 milliseconds to 3.08 milliseconds. This increase in synaptic delay and decrease in maximum MAP amplitude can be explained by adenosine's mechanism of action. Adenosine A1 receptors are present on the presynaptic terminal, and when they are activated by adenosine, they inhibit PQ-type calcium channels via a GI transduction pathway. Activation of the GI pathway inhibits adenylyl cyclase's ability to convert ATP to cyclic AMP, and decreased cyclic AMP levels decreases the signaling abilities of protein kinase A, or PKA. Decreased PKA and cyclic AMP levels inhibit the functionality of PQ channels. When these calcium channels are inhibited, calcium influx into the presynaptic terminal decreases. The decreased amount of calcium in the presynaptic terminal decreases the amount of vesicles containing acetylcholine that are released. With less acetylcholine being released, less nicotinic M cholinergic receptors are activated, so sodium ion influx into the postsynaptic terminal is lower than control. This in turn generates a smaller EPP, which for some muscle cells is not enough to reach threshold and fire an action potential. This decreases the amplitude of the MAP since less muscle cells are initiating action potentials. In addition, the decreased amount of acetylcholine being released also means it takes more time for enough nicotinic M cholinergic receptors to be activated to generate an EPP large enough for a MAP to be initiated. This increases the MAP latency, which explains why the synaptic delay increases. Dantrolene is most commonly known as a muscle relaxant and can be used to treat muscle spasticity. Dantrolene works by inhibiting ryanodine receptors in the sarcoplasmic reticulum, preventing calcium from flowing from the sarcoplasmic reticulum into the cytosol of the muscle cell. Decreased calcium in the cytosol causes the muscle to relax, as fewer cross bridges are able to form. Based on this mechanism of action, we expect dantrolene to have no effect on the neuromuscular junction, since the sarcoplasmic reticulum is downstream of the NMJ. However, our results show the synaptic delay increased from 3.34 milliseconds to 3.51 milliseconds, while the amplitude of the maximum map decreased from 2.445 millivolts to 2.405 millivolts. The slight decrease in map amplitude can be explained by the muscle's contact with the recording electrodes changing. Since the muscle twitches during each contraction, it shifts around on a nerve chamber, which could cause a slight change in reading. However, the increase in synaptic delay must be explained another way. Studies have shown that there are also intracellular calcium stores in the presynaptic terminal. The endoplasmic reticulum functions as a calcium storage unit, similar to the sarcoplasmic reticulum in the muscle cell. The endoplasmic reticulum also contains ryanodine receptors that allow calcium to flow into the cytosol. When an action potential reaches the presynaptic terminal, these ryanodine receptors open up to allow calcium to flow into the cytosol of the presynaptic terminal, which helps trigger exocytosis of vesicles containing acetylcholine. When dantrolene is added to the NMJ, it inhibits the presynaptic ryanodine receptors, which prevents calcium from leaving the endoplasmic reticulum and contributing to vesicle exocytosis. With decreased calcium, the number of vesicles that are released by the presynaptic terminal is lower than control, so the concentration of acetylcholine in the synaptic cleft is lower than control. This means it will take longer for enough nicotinic M cholinergic receptors to be activated and generate an EPP large enough to trigger a MAP, which causes the increase in synaptic delay. The max MAP does not decrease because even with the inhibition of ryanodine receptors on the ER, there is still enough acetylcholine released to activate the amount of nicotinic M cholinergic receptors needed to generate the maximum MAP. The same number of action potentials in the muscle cells are initiated, it just takes longer to initiate all of them.